Okay, so today it is E field, which is strongly related to the electrostatic force. So we have the definition of E field, and we will calculate many cases for the E field that will be generated by different situation, charge particle, dipole, line of charge this, uh, something like that. So first of all, maybe I yeah, laser pointer. Okay, so the electric field. Last chapter we know that when we have two charges, Q1, Q2, no matter whether they are both positive or negative, or one is positive, one is negative, as long as there are two charges not equal to zero, they have a force interact to both of them, either attracting each other or repelling each other. And the question is, how does particle 1 know the presence of particle 2? Usually we'll find that if I was pushed or pulled by a force, so you must touch me to push me or pull me. I don't suppose that you can use 气功 to push me. If you can show me. And actually, how does particle 1 know the presence of particle 2 is a philosophical problem. And I think it is quite suitable to be discussed today because I've checked that today is still July in the lunar Canada, which means that today is still the month of ghosts. So maybe the ghost can have some kind of ability to push me without touching me. So let's continue. Okay, particles set. The explanation of this is that particle 2 set up an E field or electric field. Maybe I'll say E field is more simple to say. At all points in the surroundings, which means that not only I mean when Q2 is there, it set up a charge in the whole space around it. Although some at some point may be stronger, at some point may be weaker. But as long as it set up a field, in this case it's E field, then when we place particle 1 inside the field, actually the whole space is the field. So when Q1 is here, it will sense the field generated by particle 2. Particle 2 push on particle 1, not by touching it. It push it by the field it generates. Yeah. So here we define the E field. E field is also a vector as well as the force. So E is defined to be the force divided by Q0. So the host here is this charge, and Q0 is just a test charge, which means that the E field does not have relationship with how large Q0 is. No matter Q0 is large or small, the field at this point is the same. It's only related to this charge. So yeah, this is a very important definition, and the SI unit is, of course, newtons over coulomb. F for Newton, Q0 is coulomb, so N over Z, N over C. So here, Yeah, this is a concept to know the E field lines. E field lines help us to visualize the direction and magnitude of the E field. It is not really precise to know how large a E field is, but it visually helps us how to know help us to know. For example, for this part, as you see, the lines here is more dense, so the E field here is stronger. And for this part, the E field lines is less dense, so the E field here is weaker. So it is a visualize. It didn't tell you how large it is, but relatively it can tell you the E field here is larger than there. And for this case, all the lines are parallel. So for example, here has the same magnitude with here and there. So this is a visualize for the E field. And actually, what we need to care about is that when the charge is negative, the E field is pointing towards this particle, and if this charge is positive, the E field is pointing outwards. So for this graph, we have two charges. So this positive charge will generate some E field in the space, and for this charge, it will also generate some E field in the space. And actually, they are vectors in the space, so they may interact each other. Actually, when this charge is placed here and that charge is placed at here, then the E field at the space is the sum of these two vector fields. And actually, for this charge, if you just ignore the lower part, actually, let me. If there are no discharge, the E field generated by the upper particle will be just like this. It feels like it is uniform for different direction. And actually, if you ignore the upper particle, it also generates the E field uniformly. But of course, for this charge, the E field it generates here is weaker than here, and it will be even weaker like here. So it will have a weak influence to the total E field here. So you can try to understand like this. So for this part, it feels like it's strongly influenced by the upper particle, and for this part, it is strongly by the lower particle. But for the middle part, both particles influence here with a certain influence, so that they bend here. Actually, for example, at this point, in between the two particles, so they will generate the same E field with opposite direction, so that they cancel each other. So in this graph, you cannot see anything here. So you cannot see anything here. And when you add all of them together, it will look like this. Any question up till now? So as we has the definition, E equals F over Q0. So F is K times Q1, Q2 over R squared. So if we divide it by 0, E will be just K times Q over R squared, which means the E field generated by a particle with charge Q only relates to the charge itself. No matter how large a test charge is, it doesn't really matter. So it mentioned that if the charge is positive, the E field are all points directly away from the particle, and on the contrary, if the charge is negatively charged particle, all points directly toward the particle. Well, for more than one charged particles, you calculate the E field for every particle generate, and then you add all of them together. So this is a link which you can simply play with. You can set the two particle, how large it is, although you only have 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. But you can have a simple idea. When you have two positive charge, it will look like this. When they have different magnitude, you have some feeling about that. But as the time is very tight, so you can play with it at home. Okay. For the sample problem 1, three particles with Q1 plus 2Q, Q2 minus 2Q, Q3 minus 4Q, each with a distance D, 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 D. So what is the net electric field produced at the origin here? So this is very simple. So the E field generated by Q1 is E1. So I'll define R1 is like this. So E1 would be K times Q1 is 2 capital Q over D square R1. And E2, maybe I just define R2 in this direction. So K times minus 2Q over D square R2. And actually R2 is negative R1. because they are in the opposite direction, they are also a unit vector. So you can see that is like this. For E3, let me define R3. R3 is here. So E3 will be K over K times minus 4 capital Q over D squared, R3. So actually, E3 will be like this, and E1, E2 is, okay, yeah, we have R1 here, R1 hat here. So actually, these two are the same. And when we add E1 and E2 together, actually the magnitude of E1 plus E2 is equal to the magnitude of E3. So it's just like a triangle, and two sides are equal. And this angle is 30 degrees. So actually, what is the net E field produced at the origin? So E total, or maybe we can simply write it as E is E1 plus E2 plus E3 is 2 times K 4Q D square, and here is cosine 30 degrees. Actually pointing to the positive x-axis. So if you want to simplify it, it will become 6.93 over 4 pi epsilon 0 Q over D squared, like this, 6.93. Okay, any questions? Actually, we are still in the easy difficulty, hopefully. Any questions? Now we move on. So for this section, we try to calculate the E field due to a dipole. So what is a dipole? Dipole in Chinese is called 偶句，偶句。Hopefully, okay, my Chinese is not good enough. Okay. Okay. Dipole is actually a pair of charges. One is positive, one is negative with the equal magnitude. Two particles with charge of equal magnitude Q, but opposite signs, separated by a small distance d. This distance is fixed, so that these two charges form the dipole. And the physical variable related to the dipole is the dipole moment, which is defined as P is also a vector, equals Q times the vector D. So it relates to how large the charge is and also the distance between them. And the SI unit is coulomb meter. So in this case, it's mentioned that the magnitude of the E field generated by the electric dipole is like this. E equals 1 over 4 pi epsilon 0 2q d over c cubed. Or, as we know, qd is p, so we can write it like this. Here we need to assume that z is much larger than d, which means that the distance between them is very small. And then we want to know the E field along the z-axis, which means that we have a dipole here, and then we want to maybe one charge is here and another charge is here, and then we want to know the electric field along this line and this line, but z is defined like here is 0 and go to the positive side. This is c. This is the negative c direction. Maybe you will ask, why do we calculate the E field at the other position? The reason is it is not easy to calculate by hand. So for this formula, it only tells you that the E field generated by the dipole along this line. And also we need to assume that this z, the distance between the point you concern and the center of the dipole is much larger than the distance between the two particles, the two charged particles. So here we show you how to derive that. Actually, this is quite simple. Only some algebraic calculation. So there are two particles, right? So actually, when you want to calculate maybe the E field at z, so you calculate the E field generated by the positive charge, and you calculate the E field generated by the negative charge and add them together, and that's it. So we try to calculate like this. The negative sign means that this is a negative charge, and here we only concern about the magnitude. So this overall term is a negative because this is negative charge, so it will generate a negative E field, which means pointing downwards. And for the E field generated by the positive charge, you're pointing upwards. So actually, it's not difficult. E plus is k times q over r plus square. R plus is actually from the center to, not here. R plus is the distance between the point you concern with the positive charge, which is here. This is R plus. And for R minus, which is from the negative charge to the point you concern here. So it is a simple, it's just a simple expression. And then, so we have K, we have Q, K, Q, so we fractate out. So inside is 1 over R plus square minus 1 over R minus square. and R plus is actually Z. Z is what we concern. Z is what we concern. Minus half of D is R plus. It is simple geometry. And for R minus, similarly, it is Z plus D over 2. C plus D over 2 is R minus. Okay. So we factor Z square out, which means that we try to factor Z square out, which means that we divide Z square here. We divide Z square here. So that these two has a square. Then we'll cancel the Z. Cancel the Z. So this is 1. This is D over 2Z. And similarly for this term. So we try to subtract them, which is simply like this. Because this is 1 minus D over 2Z square, which is nothing but 1 minus D over Z plus D square over 4Z square. And similarly for this one, sorry, this is plus. This is plus, and for the second term will become minus 1 plus D over Z and minus D square over 4Z square. Okay, so some of them are cancel. So the only remaining term is this term. So simple math. And actually, remember we assume that Z is much larger than D. So this term tends to 0. This term also tends to 0. So the denominator is 1 times 1. And so here is 2D. KQ is KQ. And here is 1 over Z squared. So Z cubed. And that's it. And we know that P equals QD, so we can also have this expression. Any questions? Make sure you have fully understanding up till now, because the later part will be more difficult, much more difficult. Okay. So the first monster come. Okay. So the electric field due to the line of charge. Okay. Any question up till now? Okay. The equation for the E field set up by a particle. The E field set up by a particle does not apply to an external object with charge, which means that for the previous case we've discussed, we have a certain number of charge, 1 charge, 2 charge, or several charge, but it is countable. Whenever the charge is not countable, for this case, it is uniformly distributed on a ring, so you cannot count how many charge you have here. And actually, how we can solve this problem is using the calculus. You try to separate the ring into many small enough element so that we can regard a small element is something similar to a charge, and then we add all of the small elements together, and which is actually the integration, what you learn in the calculus class, the Riemann sum, Okay, so for this section, we'll try to calculate the E field generated by the charged ring at this axis. So a ring of uniform positive charge. A differential element. Differential elements means this part, the yellow, the orange part, ds. Of charge occupy a length ds, greatly exaggerate for clarity， 是夸张的，把它画得很大，其实是很小的。So it should be a very small element, infinitely small element. This element set up a E field dE here, so that we calculate the E field generated by this element and this element and this element, and we add all of them together, so that this is the total E field generated by this charged ring. Okay, the charge element of the opposite side of the ring. So it cancels some of the components because, as you can see here, so the E field generated by the ds is something like this. It is not perfectly parallel with the z-axis. However, you can consider, because it is a perfect circle, so you can find some actually a element which is opposite to it, and then you will generate an E field like this. Actually, when you try to cut it, it will look like this. So for the ds generate, dE is here. The z-axis is here. And for this part, maybe we can call it ds prime or whatever you like. It will generate an E field here. Actually, the horizontal component will cancel each other, so that only the vertical component are superposition, can be superposition together, so that the overall E field generated by this part and this part is pointing upward. Is it okay? Any questions? Any questions? No questions? Anybody have understood? No one. You have give up, right? Actually, the whole semester will have the difficulty like this or even more difficult. So if you give up now, then it will be a disaster. Any questions? Or do you want me to repeat any part? So I go on. So actually, okay, so we can calculate the E field generated by this ds, and we try to add all of them together by an integral. So this angle is theta. So the this distance is z, and here is small r. So this angle is theta. So that cosine theta is z over r. Right. And actually, r is z squared plus r squared, and take the square root, something like this. And the square root can be written as something to the half power. So cosine theta is something like this. Cosine theta is something like this. So this is simple. And so here is the vertical part of DE, because the horizontal part will be cancelled with somebody else. So we only consider the vertical part, and DE is 1 over 4 pi epsilon 0 K, and this is Q. This is the Q, which is actually lambda times ds. The length of this small element times the density of the charge. Yeah, here. Lambda is the line linear charge density. The SI unit is Z over M, which means that the total charge of this ring is Q. So Q equals lambda times the total length here. And you should have learned how long it is. It is a circle, so it is 2 pi r, right? So the total charge Q will be 2 pi r times lambda. But for this small element, it is lambda times ds, which is the charge here. And the distance between this point and this point is r. So r squared. So this is the first part. Cosine theta is this part. So the vertical part of DE is something like this, or actually you just rewrite this term to here, lambda z here, and r is actually the square root of this term. So its square is z squared plus r squared. So times this term is this term to the 1.5 power, 1.5 power. So actually this term can be simply written like this. Is that okay? So we need to integrate all the small elements. So the total E field generated by this charge ring is the vertical part of the E field generated by this small element, and then we sum of them together. And then we just substitute dE cosine theta by this So we have this term, and actually ds is 2 pi r. What we learned in the primary school, so that the integral have a lower limit 0 and the upper limit to be 2 pi r. So we need to calculate this integral. This is this is a constant. This is a constant, and actually this is also constant. This is not related to s, because no matter where ds is, dE has the same magnitude, which means that this integral is pretty trivial. It's something like you just integrate a, b, and maybe we have a k here and dx. So it is nothing but k b minus a, something like this. Because you integrate a constant, which is kx, right? Kx and then you substitute ba, so that kb minus ka, which is k times b minus a. So this integral is pretty trivial. So it will look like this here times 2 pi r minus 0, which is 2 pi r. And then, as we know, 2 pi r times lambda is the total charge Q. So we can simulate like this, which is the charge, which is the E field generated by the charge ring. Okay, similarly, if we assume Z is much larger than R, which means the point you're concerned is far away from this ring, then if Z is much larger than R, which means that C squared is much larger than R squared. So that C squared plus R squared is similar to C squared. Okay. Something like you have a very, very long right angle triangle. If this is Z, this is R, this is C squared plus R squared. So if this angle is very small, then this one is similar to this one, right? So actually, if Z is much larger than R, then just ignore the R square, and then we'll have C squared here, and oh, it's correct. C squared. So take the square root and cube. So we have C cube. Sorry. So we have C cube here and cancel one of the C. So we have C squared here and Q this one is pretty interesting. It's pretty interesting. Which means that if the distance is far enough, this range is just similar to a particle. Because if you regard it as a particle, you just smash it into a point, and then you still keep the Q, and actually you still have 1 over 4 pi epsilon 0 Q over V squared. This is what it would want to show.有没有问题？我们继续吧。Okay, 22.03. So for this one, a plastic wad have a uniform distributed charge minus Q on this rod. This wad has been in a 120-degree circular arc of radius r. 是一个扇形120度的。Replace coordinate axis such that the axis symmetry of the rod lies along the x-axis. The origin is at the center of the curvature P. P 是它的圆心 P is the center. P is the center of this rod. In terms of Q and R, what is the electric field of the rod at point P? So, so we also separate the rod into infinite small decimal, so that small element, so that we have ds here. And actually, the E field generate actually the charge is minus Q, so that the E field generated by the small element is pointing toward the element. So we have ds here, and also we have the symmetry part at the bottom, so that the horizontal the vertical part will cancel each other, but the horizontal part will be add together. So actually, dE would be something like 1 over 4 pi epsilon 0 lambda s lambda is the density, lambda ds lambda ds, and the distance is r, so r squared at the denominator. And we concern the horizontal part. So dEx is dE times cosine theta. dE times cosine theta. So like this. Lambda ds r squared cosine theta. Actually, ds would be the radius times the angle, the infinite small angle in radian. shown here. ds is r times d theta. So we substitute this term here, which will becomes 4 pi epsilon 0 lambda d theta cosine theta, which means one of the r is cancelled. And then we want to calculate the total E. This is dEx. This is dEx. So E would be the integral of dEx. dEx. So actually, this is 60 degree, which means that the angle is from minus pi over 3 to pi over 3. And we have k, which is 1 over 4 pi epsilon 0. And we write it lambda cosine theta over r d theta. Actually, most of the terms are constant to theta, k lambda r. So, which is nothing but k lambda over r. And we integrate the term cosine theta, d theta. So this is nothing but sine theta, pi over 3 minus pi over 3. So the answer here is square root of 3 lambda 4 pi epsilon 0 r. Not yet. Actually, we still need to cancel the lambda because we know the total charge is q, minus q or minus q. So minus q would be, or maybe we can write q will be the length of this rod is 2 pi over 3 times the radius. 2 pi over 3 times the radius. R. 2 pi over 3 is pi over 3 here minus negative pi over 3. So 2 pi over 3. So 2 pi over 3 times r is the length of the rod times the density lambda. So we have q equals 2 pi r lambda over 3. And which leads to lambda equals 3q over 2 pi r. And we substitute lambda to here. So it turns out the answer will be 0.63 q over 4 pi epsilon 0 r squared. Oh, yeah. sine 60 degree. K 就是1/4 pi epsilon 0。I see. K over lambda R. Okay, you can simply ignore this part. You can simply ignore this part. K lambda R. K is 4 pi epsilon 0. Lambda is here. R is here, and then this part is square root of 3. This part is square root of 3. Okay, we need to go faster. Oh, actually, I don't really need to calculate in a single page. So this checkpoint is just to tell you how you can cancel something. The cancel the part you can cancel, and well, so for part A, it asks you which direction the total E field is pointing at. And actually, it is quite simple. For the charge, for the E field generated by the lower part, it will point this way. For the E field generated by the upper part, it will point this way. So the horizontal component will be cancelled. So this one pointing upward. And for B, pointing right. I think it's quite trivial. Pointing right. Because, for example, this part like this part like this. So the vertical part cancel, so only pointing right. And for C, it will be something like this, so it points downward. Okay. Watch. Wow. Okay, so we move on. So just now we calculate the E field due to a charge ring. Now we calculate the E field due to a charge disk. Just now it's a ring, and then the radius of the ring varies, and then they add together so that it will become a disk. So you can imagine the ring has a radius from 0 to capital R, and then you add all of them together, then it will become a disk. That's why it writes, sorry. So that's why it writes something like this, which is actually from here. From from this 22.16. This one, 1 over 4 pi epsilon 0 qz over this term to the 3 over 2 power. So it will become this term, exactly the same. And actually, the total charge here is also Q, I think. So the charge at this ring is only dq, and the E field at here is here, and z the coordinate is z. So which means that it's the distance between the point P has a distance z with the disk. Okay. Then you try to integrate this from 0 to r. It will become that. So here you have this, and actually you still need to do some trick. dq is something like sigma times dA. dA is the infinite small area of this ring, and the area is actually 2 pi r times dr. Actually, it's a ring, but you pretend it is like a rectangle. You try to cut it out, and then as the dr is infinitely small, you can estimate the area of this ring to be 2 pi r, which is the length of this ring times the height. The height is dr. So dA would be 2 pi r times dr. And sigma is the surface charge density. Just now the line charge density. Now is surface charge density. So the SI unit is C over m squared. And now, so you substitute dq to here, and then you integrate this from 0 to capital R, and that's it. Something like that. So simple calculus, so I don't spend too much time on it. So the answer will be something like this. And here we assume that if this disk is infinitely large, the E field would be simply like this. This is quite important, which will appear in the later chapters. Maybe the next one and the 2 chapters later. Well, when r tends to infinity, so this term turns to 0, so only 1 times this term, so only E is something like sigma over 2 epsilon. And the interesting part is that the E field generated by this disk is uniform, which is quite strange. Doesn't really match to our intuition. We may think that the E field generated by the disk will become weaker and weaker as the distance becomes larger. But here we assume that the disk is infinitely large, so the E field in the space is uniform. So this is an example so that, okay, it's actually, originally we have E equals F over Q, so we just multiply Q on both sides, so we have F equals QE. And here it shows that for the inkjet printer, it has some ink here. Maybe this one is green. When it input here, it adds some charge on the ink. And here we have a uniform E field. That's why it shows this part. It generates E field. How it generates here is assume that this is a infinitely large charge plate, so that the E field with between these two plates is assumed to be uniform here. Okay, so it tries to control the charge add to the ink, then the ink will be accelerated by the E field, and then it turns a little bit to this direction. If you don't add a charge on the ink, it will go straight, and then this is the paper you want to print. So it tries to control the ink by adding some charge on it, and then it will rotate, and then go to the desired position. Actually, this example is quite easy, so I just skip it. Maybe I can come back next week. I can have a quick review next Tuesday, but I hope I can finish most of the content about chapter 22 and chapter 23. This one is not so important, but I just go very quickly. As mentioned, we have a dipole Q minus Q and Q. This is a dipole. When it is in the uniform E field, it will have a torque. Torque is Bg. So it will try to rotate, right? Because in an E field pointing with an E field pointing to the right, so just ignore the negative charge. The Q will try to going the right side, and for the negative charge, it will try to go to the left side. So it will just something like this, right? So it will try to rotate. This is what we call the torque. And actually, the mathematical equation is P cross E. It is the cross product, the right-hand rule, cross product. So if P, maybe I just saw it, yeah. Well, maybe how to say? Well, yeah. Actually, P is pointing that way, and E is pointing the right side. So actually, P cross E would be something like this, and cross E, and then pointing inside the product. So the torque will be pointing inside, something like this. The cross means pointing inside. If it is a dot, it's pointing outside. The direction of the torque means it's rotate with respect to this axis, something like this. And the potential energy up to now, I don't think is very important, but the the point is something like the potential energy is minus P dot E. Dot is the inner product. So it is nothing but PE times the cosine theta, the angle between them. Which means that well, not so important. So maybe we will discuss about this topic later. Additional problem 1, 2 is quite simple. Maybe I will do it on Tuesday.